high rate of penetration, low pump rate, no circulation. Those are poor drilling practices. So as mud engineers, we need to know all these things, because when they drill at a very high ROP and they are not able to circulate, or they are experiencing tug and drag, at the same time, they did not circulate very properly during connection, the first person they will come and meet is you. If you're on the rig and you see that they just carry down one stand, and immediately, without circulating, without reciprocating the string, immediately they are making connection to go with the next one, raise an alarm, meet the company man, excuse sir, how many bottoms up are we making after every connection? Ask him that question. How many bottoms up are we making after we carry down or at connection? How many bottoms are we making before drilling the next stand? Those are the questions you will ask him. Are we following?
Yes.
Okay. Now, when you begin to have all these cuttings settling down, what you have is called cutting bed. What you have is called cutting bed. Cutting bed builds and slides downhole, packing off the string while pulling out of hole. The cutting bed is dragged upward by the BHA and pack off the drill string. What do we mean by that? Like I said in the previous slide, your cuttings are coming down. Your cuttings are coming down. There are situations whereby the cuttings have covered your BHA. And as you begin to pull and pull and pull, the driller begins to pull. If he exerts so much over pull, before you know, you have parted the string. Your BHA is in the well while your empty string is out. The only remedy is, there's what they used to say, burial ceremony. Have we heard of burial ceremony before? Hello?
Yes.
Okay. The next option is the next option is burial ceremony. They have to plug the hole outside track. The BHA is there. They have buried the BHA, which is very, very costly. That's why they say it's a ceremony. It's not a pleasant one. This happens especially in deviated holes where you have the angle greater than 35 degrees. You have cutting beds. But in the case of vertical hole, it will just go down. The cuttings will just go down. In the case of deviated holes, that angle where you have the 35 degrees, remember, it will not just be at one point, it will be a column, a length of columns. That's where the cuttings will go and settle. The string will be above, while the cuttings will be below. Differential sticking will be there, and mechanical sticking will be there as a result of cutting beds. How to improving hole cleaning efficiency? Hole cleaning factors. What are the things that one needs to consider? What are the factors? Who is responsible for cleaning the hole? What are the things that we need to look at to ensure that the hole is cleaned, to ensure that the pipe goes in and out freely at will? Some places you see, they will log for 5 days, no circulation. The company man will be giving updates, 170 hours, last circulation, 205 hours ago was the last circulation. And they're able to go in and come out without any issue. All is in good condition. No tug, no drag, no held up, no nothing. Those are the kind of things that mud engineer likes to hear. I remember a mud engineer, he says, when he looks at the company man's report, the thing he likes to see is hole is smooth. No tug, no held up, no tight spots. Those are the things we should be aiming at. One, the mud engineer is responsible. The drilling engineer is responsible. When we talk about the drilling engineer, not just the one on the rig, but the one in town that plans the well alongside the well planners, and the driller is responsible. Now, when we talk about the mud engineer, what is the mud engineer's responsibility? Ensure that your mud weight is right. Ensure that your mud weight is right at every point in time. I've met a mud engineer that says, when we are running a 10.0 ppg, the mud weight is increasing and it's doing nothing. It's 10.5, no issues. I told you now it's 10.5. Meanwhile, they are talking about 10.0. And before you know it, boom, losses have started. Before you know it, the string will get stuck. Because 10.5, the flow rate is different. For a 10.5, there is a flow rate that is supposed to go with it. For a 10.0, the solid content is less than a 10.5. So your mud weight must be right. Your rheological properties must be right. Your viscosity, your YP, your gel strength must be in good shape. Then we look at mud viscosity. The mud viscosity too has to be in good shape. Then when you talk about the angle, now the angle, the drilling engineer in town plans the angle. Where is the reservoir? Where do we want to assess the reservoir? How do we want to assess the reservoir? The reservoir, is it a very rich one? If it's a very rich one, maybe we can go with a deviated hole. It's a little depleted, so let us go with it on horizontal. Oh, this reservoir is very rich. We want to maximize it. Let's go horizontal. Oh, we can still go deviated. We can still go deviated in a particular angle. We will still get maximum flow oil. The reservoir is very big. There's no point going horizontal. We can go deviated. If we go horizontal, it's almost the same. The reservoir is very thin, so let's go horizontal. Those are the factors that the drilling engineer will be considering. The length of inclination, the reservoir, what length, what angle do you want to keep there? That the drilling engineer, the company wants to keep at that point to maximize production. Well geometry. Okay, for well geometry, we have the oil, we have the reservoir at 3,500 meters. That's where we have the reservoir. How do we build our well geometry? Should we start with 26-inch hole, 20-inch casing? Then we'll get to a particular point, switch over to 16 or 17.5-inch hole, 13-8 casing. From there, we enter the 12.5, 12.25, 958, and then we go into the 8.5, the 7-inch liner, or 7-inch casing, as some companies will do it. How do we want to do it? How do we apportion? At what point do we land our casing? Definitely, you must land your casing in a good clay or a good shale, not in a sandy area where you have so much losses and your casing will not be very firm. The integrity of the casing will not be questionable. You want to land it where it's very firm, it's standing, and nothing is shaking it. Those are the work of the drilling engineer in town. Then when you talk about the driller, there's a lot the driller has to do. What is the flow? Ensure that the flow you're giving is the correct flow. The pump efficiency has to be right. The pump has to be at least 97, 98 to 99% efficiency. So that when you say that I'm pumping at so GPM, it is so. I'm pumping at so and so strokes, it is so. It is so. Circulation time. Circulation time. What's the circulation time? You have to know surface to surface. Please, just a moment, I will be back. Just a moment. Hello, sorry for that break. Okay, I was talking about the circulation time. The driller has to know, not just the driller, as a mold engineer, you need to know what's the circulation time from surface to surface, from surface to bottom, from bottom to surface. What are your circulation times? For example, if you pump a peel, you need to know when the peel is coming up. You make connect, you have drilled to, you have carried down one stand, and you want to, you're doing one bottoms up. You need to know the amount of time it takes the cuttings from the bit to the surface to ensure whether the hole is clean to some extent. Rate of penetration, that is the driller's work, but the mold engineer too has to know if the drilling engineer has programmed 20 meters per hour drilling, and you see that the driller is going 22, 25 meters per hour, look, raise an alarm. Yeah, don't say the driller, oh, this driller is drilling very well, we are tearing the hole, we are doing, it will fall back to you. So raise an alarm. Sir, meet the company man, we are on 25 meters per hour. How many bottoms up are we going to make at connection? Or when we're curling down? Those are the questions you'll begin to ask. And again, rate of penetration, as it is increasing, know that your solids are increasing as well. And you need to be able to handle your solids in the mud. Your cuttings, you should be able to handle their removal. Let them not be forming more than you can handle. Pipe rotation and reciprocation, those are things that ought to be done by the driller. At the proper rotation, for high angle holes, you'll discover that you need to rotate your string more than when you're drilling vertical or straight holes. Are you reciprocating the string when you're doing your bottoms up after curling down? Those are things you must check. Some rigs have one problem or the other with curling, when they curling down, rotations and the rest. Maybe the rotation is not actually what it's supposed to be. 80 to 100 RPM. Maybe they are making 70. Those ones too affect, because as they are rotating, they are agitating the cuttings and the flow is picking them up. They are not allowing the cuttings to settle down. Formation, what kind of formation are you drilling? There are some formations that the cuttings will come out very fast. If you're drilling through a sand formation, you observe that the cuttings will be small, tiny cuttings. And when those ones settle, they become like cement. But there are some formations, hard clays, shells, you see them coming out in their beads. 1/2 inch, 1 inch, 1/4 inch, 200 micron sizes and the rest. So the formation too, you need to know. Are you drilling through sand? Are you drilling through WBM, or are you drilling with WBM or OBM? Those things you need to know. Cutting size also matters, and density. You may be drilling through sand, you may be drilling through clay. You remember, if you're drilling through clay and you're using a WBM, it will just be coming as though it's sticky. Sometimes when you're drilling through clay and sand mixtures, formations like that, you may not see the clay, you may see it as sand. The clay will just be swallowed up, mixed into the sand. And as a mud engineer, you may not know that clay is actually coming out. And clay are fine solids. They will just be building up in your mud, And you know, when you're drilling with an OBM, OBM tolerates solids very well. Some people say it's OBM, nothing is happening. OBM tolerates solids, it can accumulate these solids, it can hold them very well and still be flowing. But it will get to a point whereby it will gel up. And when it gels up, the string is the culprit. So as mud engineers, we need to know all these things so that our work will be easier. We are looking at annular velocity. What is the annular velocity? Is the speed or the velocity at which the cuttings are traveling up the well. Annular velocity is the most significant factor impacting hole cleaning that minimizes cutting bed height. It minimizes cutting bed height. And remember, like I said earlier, your angular velocity must be greater than your slip velocity. It must be greater than your gravitational velocity. It must be greater than the velocity at which your cuttings are coming down when in the static situation. Now, I want us to know that if your cuttings are bigger, the slip velocity will be higher. If your cuttings are bigger, the angular velocity may be lower compared to smaller cuttings. And with respect to the flow rate, angular velocity is below 131 feet per minute equals to bed height occupying greater than 40% of the annular space. Let me take that again. Angular velocity below 131 feet per minute. 131 feet. I want us to think about how long is 31 feet. Take your plot of land. Some plot of land is 120 by 60. Some is 100 by 60. Imagine that that one is standing. Imagine that that one is standing. It says in 1 minute, one cutting is supposed to have moved. Supposed to have gone up. And if your angular velocity is less than this 131 feet per minute, it then means that even though your cuttings are coming up, it is occupying more than 40% of your annular space. Your annular space is the space between your pipe and your wall, the wall of your well. You're drilling a 17.5-inch hole size and your drill pipe is 5.5. You have some space. But let's take your drilling 8.5. Your annular space is very small. 8.5 and 5-inch OD drill pipe. Your space is just 1.5 on each side, 1.5 feet on each side. It's very small. Or you're drilling a 6-inch hole drain hole section, and you're using a 4-inch pipe, 4-inch OD pipe. You just have 1 inch on both sides, very small, very, very small. So if you have an annular velocity greater than 262 feet per minute, then it equals to bed height occupying less than 10% of your annular space. Invariably, your hole is clean. That's what we are saying. The essence is ensure that your hole is clean. Do all you need to do to make sure that your hole is clean. Some companies normally run sweep, pump sweep. After every stand, they pump sweep. 50 barrels of sweep, 20 barrels of sweep, 25 barrels of sweep, just to ensure that the hole is clean. Now, some mud engineers tell them the hole is clean. We just want to confirm. We just want to ensure. We just want to gives a second confirmation that the hole is clean. Pump the sweep and let's see it come out. It will bring out all the smaller, finer cuttings and solids out for you. Pipe rotation. Drill pipe rotation minimizes cutting bed. It minimizes cutting bed. How? As it is rotating, it is agitating. As it's rotating, it is agitating. It is reducing the slip velocity. It is not allowing it to settle, especially at the angle areas. It will not allow the cuttings to settle. Its effect is significant at low annular velocity and high angles, especially when the annular velocity is low and your angle is high. You know, when you're drilling some hole, some 8.5-inch hole, you discover that you'll be drilling at things like 250 GPM. Some places you want to drill at a controlled speed. As such, the flow is very low. So at this point, pipe rotation also helps. Eccentric drill pipe impacts the drill pipe rotation positively to reduce cutting beds. Eccentric drill pipe, when the drill pipe is at one corner, but it is not stuck, you see that you have enough space at one point where the cuttings will be traveling. Where the cuttings will be traveling. Increasing drip pipe diameter also optimize the effect of drip pipe rotation. Increasing drip pipe diameter also optimizes the effect of drip pipe rotation. Drip pipe rotation is incredibly desirable and effective at angles of 60 degrees or greater. For angles of 60 degrees or greater ones, you must have good drip pipe rotation. Your drip pipe must rotate very well. Your drip pipe must have a good rotation. Mud weight. Now we are looking at high angle and extended reach drilling. Mud weight. How does your mud weight affect hole cleaning? Improving your hole cleaning is what we are talking about. Hole cleaning efficiency. Mud weight has one of the most significant impacts on hole cleaning due to its buoyancy effect. You know, now when you have viscosity, let's say you have a viscosity of 70 seconds per quart, low weight, unweighted mud, 70 seconds per quart. By the time you weight it up, you will discover that the viscosity has increased. By the time you weight it up, say you are having 8 ppg and you weight it up to 9.5, check the viscosity again. You discover that it has increased, especially with OBM. So now, for the fact that the viscosity has increased, it gives the cutting some buoyancy. It gives the cutting some buoyancy. Some companies make use of this mud weight. When they are drilling, once they finish drilling and doing all the necessary precautions as per drilling, they pump an heavyweight mud. They pump a heavyweight mud to clean the hole finally. They may be drilling with a 10 ppg mud, but you discover that at TD, before wiper tree, before pull out of hole, they will pump a 12.5 ppg mud. They pump slug. And that slug, because it is heavy, it is viscous, it will carry everything. Just like in this case of cementing, the lead slurry weight is lower than the tail slurry, because the tail slurry has to push. It has to exert enough force to push. It has more buoyancy to carry the lead slurry. Same is in the case. When your mud weight gives the cutting some buoyancy. Low mud weight equals to 40% cutting beds height in the annulus. High mud weight equals to less than 10% bed height in annulus. What we're saying is mud weight also helps in cleaning the hole. It gives buoyancy effects. It helps, it collaborates with your viscosity to carry your cuttings up the well. With increasing mud weight, study shows that cutting bed sliding diminishes. With increasing mud weight, your cutting beds, the formation of your cutting beds will be minimizing, will be reducing. So if the possibility of having a cutting bed is less when you are drilling with a 10.5 ppg mud than when you're drilling with a 9 ppg mud. Hole angle. Improve hole cleaning efficiency. We are looking at the hole angle. With 45 to 60 degrees, the most challenging angle to clean is the most challenging angle to clean. 45 to 60 degree angles are the most challenging angles to drill with time in dynamic situation, because the cuttings will be sliding down continuously. They have a place where they can easily rest, no issues, no need for to go up. Remember, take for example, when you're making a turn, you're driving on a straight road and you're going with same speed. You're going with same speed and you meet a bend. The normal thing you will do is to reduce your speed. If you continue with your speed, you will hit the other end of the road. And even if you're going with same speed, as you hit the other end of the road, you discover that it bounces. It bounces to the other side of the well, bounces to the other side of the well. Angular velocity is reduced. Angular velocity is reduced at those angles, those particular angles, at those curves. The angular velocity will be reduced. There's no two ways about it. That's why most companies, when they are drilling and they are in high angle holes, they like pumping sweeps. They like pumping tandem pills. A low weight, high weight, low viscosity, same mud. Some of them will just pump base oil and continue. Some will pump base oil and pump a higher weight mud just to compensate the hydrostatics. Between 75 and 90 degrees, cutting beds are maintained uniformly in height over time and become packed. So between 75 degree angles and 90 degree, they form evenly. They'll be forming, it will be there. But in the case of 45 to 60, it will be at that point. That particular angle, that place that the angle curves very well, that's where it will be. But in the case of 75 to 90, it will be all true. The cutting beds will be there. The height will be there, same thing. Let me move over to the next slide. Rheology, effective at reducing cutting bed height. Angular velocity, high angular velocities help improve the effect of rheology. The effect of rheology on bed height is less evident in high angles between 45 and 60. Now, what we are saying here is that your rheology, if your rheology is right, it works with your angular velocity to clean your hole. If your rheology is high, right, it cleans the hole. Your rheology, what are we talking about? Your YP, most especially. Your YP and your funnel viscosity. Remember, funnel viscosity is just to give you an idea of what your viscosity looks like. Your YP is telling you what is actually working. If your YP is right, it works in collaboration with your angular velocity to give you good hole cleaning. That's why when you look at your mod program, you discover that every hole section, every hole size has its own YP or rheological property range. Cutting size. The impact of cutting size is dependent upon cutting density and ROP. Doubling the cutting size and ROP may double the bed height unless one or more of the significant variables are optimized. Now, the more the cutting size increases, the more the tendency that there will be cutting bed. Definitely a half-inch cutting size will have more tendency to slip down more than a 200 micron size. The bigger the cutting size, the more it slips down, and the more the cutting bed will be high. Now, it says, if your cutting size is high and your ROP is also increasing, you're drilling fast, you're drilling a 12 and a half inch hole section, 12 1/4 inch hole section, and you're drilling very fast, and you're drilling through shells, and they're coming out in sizes well inhibited, your cutting beds will also be increasing at any point in time. If you make mistake and stop the pump, there's every tendency that you have a stock pipe. Now, if your cutting size is big and you're drilling with a high, your ROP is high, it then means that your annular velocity too must increase. How do you increase your annular velocity? It means that your pump pressure too must increase. Your flow must also increase. Your mud weight density too should increase with respect to the formation pressure. That's how cutting size affects hole cleaning. The bigger the cutting size, the tendency for cutting beds to form. Drill pipe eccentricity. When rotary ROP is applied, the eccentric position of drip pipe is desirable in high angle. Eccentric is desirable in high angle. I want us to look at the diagram below. This is an eccentric one, deviated hole, and this is another one in deviated hole during sliding. This is a concentric vertical hole. When you're drilling, my cursor is on the eccentric diagrams. When you're drilling in high angle holes, if your drill pipe is at one corner, is at eccentric position, it gives enough space for the cuttings to travel, especially in high angle holes. But in a vertical hole, it's better this way, in a concentric position, because there's no opportunity for cutting bells. Rather, in a vertical hole, we have settlings. When the pipe position is eccentric, the effect of rotary ROP on hole cleaning is most significant. When drill pipe is concentric, annular velocity tends to reduce cutting bed height more effectively. Rate of penetration. High rate of penetration is sustainable if the size of the cutting is small. High rate of penetration is not sustainable if the cutting size is large, unless the significant variables are optimized. Now, when we're talking about these significant variables, we're talking about pump, pipe rotation, mud weight, and the annular velocity. When we talk about annular velocity, we are just talking about the flow, the GPM, 450 GPM, 750 GPM, and the rest. You see that if you start drilling the surface hole in the WBM, they start with 250 GPM, 250 GPM, like that, because the top hole is unconsolidated, and mainly you will just be seeing sand coming out. But as they go deeper, as they begin to cut, as they begin to meet clay, you discover that the flow begins to increase with depth. Pipe rotation too has to increase. The mud weight too will be increasing, like that. It is very difficult, or let's say it's not easy, drilling through a section with same mud weight, even though the formation pressure allows it. It's not easy. So one of the variables, significant variables, must be optimized. When they talk about optimize, it must be increased. It must go to this maximum. If your flow is 450 to 500 GPM, take it to 500. And if the formation pressure allows it, you can go beyond, as the drilling engineer will say. Drill pipe size. Drill pipe diameter has minimal effect on cutting bed height. Drill pipe size has minimal effect on cutting bed height. The effectiveness of rotary RPM is impacted by drill pipe diameter, and cutting size. So the major thing is let the pipe be rotating. RPM is the most important thing. You can be drilling with a 5.5 inch OD drill pipe. You can be drilling with a 5-inch drill pipe, no problem. But sometimes when you're drilling 6-inch hole, depending on the depth, you could decide to go with a 4-inch drill pipe. Of course, it doesn't make any logical sense to drill a 6-inch hole with a 5-inch drill pipe. You could decide to go with a 4-inch or 3.5-inch drill pipe because of weight, the weight on beat, and the rest. Barite sag. Barite sag is recognized as a significant hazard in deviated wells using both weighted oil and water-based drilling mud. Whether in OBM or WBM, barite sag is an hazard. And you begin to have barite sag if your rheological properties are not in good shape. As a rule of thumb, anytime you have your gel 0 less than 4, just know that the possibility of barite sag will be there. If you have your gel 0 less than 4, just know that the possibility of barite sag is there, especially when you are having weighted mud. How do you know that you have barite sag? When you're circulating, that you're drilling or they are circulating, and you're drilling with a 10 ppg mud, at a point you're seeing 9.8, 9.5, sometimes you're seeing 10.2, 10.5 coming out, know that there is barite sag. And you're not adding anything. Whether you're adding barite or not, just know that there is barite sag. Or in your mud pit, especially in your reserve, you have added the required amount of barite to weight up, and yet you're not getting it. Your barite sag, check it, your rheological properties are not in good shape. Barite sag fundamentals: dynamic or static lumping of weight materials in the annulus, resulting in barite sag. You have this thing sometimes when they run in, if they do a wiper trip, when they run in, they will tag bottom before the depth, before the major depth. They will tag bottom before the major depth because barite has sagged. The majority of barite occurs under dynamic condition in deviated wells. Majority of barite sag occurs. So when you're adding your barite, ensure in the OBM, ensure that you have your wetting agent to accompany it, especially if your addition of barite is significant. I'm not talking about you just had one sack of barite, you're wetting up from 10 to 10.2. Ensure that you have enough wetting agent and ensure that you're adding the barite properly. Ensure that your rheological properties are in good shape. Barite bed caused by dynamic sag tend to lump down the well during static period, causing density variation, like I explained earlier. Sag beds behave differently and have different characteristics to cutting beds. At low solid concentration, settling occurs in a segregated way, whereas settling occurs block-wise in relatively low velocity, in relatively low velocity in high dense condition. During sag, the denser, larger properties settle first, causing the overlaying fluid to be lighter and more buoyant. So you're drilling and there is barite sag, your solids will go down quickly. Your barite, the heavier ones, you know, they will settle down according to their densities. They will be settling according. Remember, you're drilling, and if your variables are not right, you will begin to have settlings, sag, and it will be coming out in different weights. Sometimes you have cuttings coming out very well. Sometimes you will not have cuttings coming out. When you have lighter fluid coming out, 9.5, you will not have much cuttings. When 10 is coming out, you have good cuttings. Cuttings will coming out normal. When 10.5 is coming out, you have so much cuttings coming out because of the buoyancy of this mud weight. Sag can occur in any well deviated more than 30 degrees, with its effect more pronounced in wells with a deviation of 60 to 75 degrees. So sag, if you have a deviated well, if the angle is higher, your sag is more. It's more. The fluid type too also matters. Your fluid type also matters. If your fluid is less dense, barite sag, possibility of barite sag will be there more. Sag increase with time. Barite sag increase with time. Oh, you just added barite now, 30 minutes ago. Oh, is barite sag? No. It increases with time. The 4 zones of barite sag are there: the lump bed, sediment bed, suspended zone, and clarified fluid. You have the lump, big lumps at the bottom, they will be coming. You have the sedimented zones, the ones that have settled, you see them coming out. Then you have the suspended zones, those ones too will be coming out. The clarified zones, the ones that have lesser mud weights, they'll be coming out as well. Key parameters. Parameters we need to look at when considering barite sag: hole angle and length, annular velocity, pipe rotation, fluid regime. Is it a laminar flow? Is it a turbulence flow? You know, at a high angle, it's preferably to have a turbulence flow. Mud density, mud rheology, mud weighting materials, particle size and shape, particle concentration, and time. When we talk about time, concentration and time, how long did you leave the well? Static. How long is the flow? Influencing factors. Barite sag is principally controlled by dynamic flow. If you have a good flow, your barite will not sag. If your rheological properties are in good shape, your barite will not sag. Mixing, addition of barite too also matters. If you mix properly, your barite will not sag. If your mixing pump is good and working well, strong and efficient, your barite likely will not sag. Influencing factor. Higher oil water ratio of oil mud. The higher the oil water ratio, the greater the barite, the sag potential. The higher the oil water ratio. Now somebody will say, why? Oil water ratio is very good, but when your oil water ratio is high, you discover that your mud is very light. But then your rheological properties also have to be good. Oh, my mud is very light, it's very good. What are your rheological properties? Are they able to carry the barite? Now, remember, barite is acting as an inert solid, and it needs to be water wet. If you don't have enough water to wet the barite, so for the barite to mix very well, then the possibility of barite sag is there. You need a wetting agent to also influence it. Mud weight fluctuations. Any inexplicable variations, that's your mud weight variations. You're drilling at one point, your mud weight is high, another point, your mud weight is low. Just know that barite sag is there. Tug and drag, mud losses and gain. All those ones also affect barite sag. You're having mud loss, your mud weight is coming out not steady. You need to do something about it. Add wetting agent, add the secondary emulsifier if you're running an OBM, add some some fluid loss materials that will mix with the barite in WBM and in OBM section, in OBM mods. Add some things that will work with the barite. So let it not just be that you just have barite and your base fluid and your viscosifiers. Give it some other low circulation materials to hold it. I want to move a little faster because of time. Mod properties and testing. We have the rheology, primary. This is an advanced mod school, so I may not be explaining some things. I assume that we know those stuffs. Rheology and primary mechanisms. Primary mod properties control mechanism for barite sag. What are the primary mod properties you use to check? The low shear rate. In our GMRs, we will see the low shear rate after the 3 RPM. It has a range. So we see that when you have a range of between 7 to 15, you see that you will not have barite sag. Like I said, as a rule of thumb, anytime your gel strength is going below 4, your gel 0 is going below 4, there's every possibility that you have barite sag. The class is supposed to be 1 hour, but we already passed 1 hour. That's why I'm trying to move a little faster. Lubricity. Lubricity of drilling fluid is measured by its coefficient of friction. The lubricity of filter cake is an essential factor to prevent stock pipe in extended reach and high angle. Now, when we talk about the lubricity of fluids, you know, the pipe is rotating. The pipe is rotating. When it definitely, as the pipe is rotating, as drilling is going on, it will be hitting the walls of the well. As it hits the walls of the well, it should just, you know, it should just rotate near it, come back. The pipe is not always static, it's moving, dangling from one point to another. When it gets to one wall, it should continue its rotation, move away. It shouldn't stick to the walls. It shouldn't, the filter cake should not hold it. That is what we are talking about, the lubricity. The filter cake should not hold it. At high angle holes, the pipe should be able to move along the filter cake without being stuck. If it is stuck, it means that our filter cake is too much, it's too thick. It's not thin. It's still permeable. It still has so much fluid in it. So poor lubricity will cause pipe stock for you. Poor lubricity of mud could cause pipe stock for you. So at every point in time, your mud has to have enough lubricity. There is a particular way that one can test for lubricity. Rule of thumb, from experience, do your 600 RPM with your rheometer and your 300. If it gives you exactly the same, plus minus, then know that your lubricity, your mud is highly lubricated. This is rule of thumb. Some of the rule of thumbs are not in API standards, but from experience, run your 600 and 300 RPM in your viscometer. If it gives you the same, then know that your mud, the lubricity of your mud, is good enough. Influencing factors.
Hello, sir. Hello, sir.
Yeah.
Please, I think you said if the 600 and 300 are same, the lubricity is good or is bad.
Okay, now you want to just, as a rule of thumb, you want to have an idea if your mod, the lubricity of your mod is okay. You know, when you're doing your rheology, you run 600, right? You run 300. Assuming you get 600, you got 60. 300, you got 35, right? Run it again, do it again to see if you will get 60 for 600 and 35 for 300. So if you get about same, you are running your rheology and you are getting the same thing, 300. You can have a little rest of mind that, okay, the lubricity of my mod is good. But you run your 600, is giving you 54. You run it again, it's giving you 60. You run it again, it's giving you 65. That same mod. Then you should be thinking about your lubricity stuff. Just a rule of thumb anyway, from experience. It may not be in the API, just like if your gel 0 is anything less than 4, with respect to mod weight. No matter your mod is bad, with respect to mod weight, your gel 0 is going less than 4. Barite sag, possibility of barite sag will be there. If your YP is not good enough. Remember, your YP and your gel, they are not same. So we continue. There are some figures here to give a coefficient of friction values for OBM and WBM with respect to the calculations. Types of lubricity. Pardon me, I'm taking it very fast. Types of lubricity. There are two types of lubricity, liquid and solids, which may be used singly or in various combinations. Now we talked about environmental concerns and mod compatibility determines the uses of each. Now there are two types of lubricity. Lubricity, you have solid lubricators and you have liquid lubricators. Now, for liquid lubricators, we know the mod lube, we know the let me say mod lube. Let me just use the word mod lube. Mod lube is a liquid lubricator for WBM. In OBM, you also have your base fluid. Now, when they talk about lubricity in OBM, it is because they have barites. They talk about lubricity more of high weight mod. When your mod weight is on the high side, they begin to talk about your lubricity because the solid contents of your mod is very, very high. It's very, very high. That's why as your mod weight increases, it is also very, very advisable to increase your oil-water ratio. Then you also have solid lubricators. Example is your Saltex, graphite. They have things they also call beads, very, very small particles, beads. You can throw these things into your mod. Beads, you can put it in your WBM, you can put it in your OBM. It gives you lubricity. It gives the pipe lubricity. The pipe will be able to move. It will be buoyant. It will be inside the fluids, inside the well. It's part of the mod, so it will give you some lubricity. I remember some years ago, 2019, Agip was requesting for it for one of their land and swamp activities because of the high angle wells they were about to drill. Beats, mod companies have it, and they manufacture it and supply it at request. So this place is this one, liquid lubricators. It's a list of different types of lubricities, lubricant we have. They are fatty-based, oil, fatty-based, solid lubricants, slick slide asphaltenes. Some of them are trade names. Some of them Aspartame is a common name. It's an IPAC name. Sulfoplast, that's a trade name. Graphite, like I earlier mentioned. Graphite, Saltex, especially graphite. Graphite is very good. You can use it for WBM. You can use it for OBM as well. If the operator permits, you can use all these things. It is the responsibility of the mud engineer or the mud company to propose the lubricant for their wells. Lubricity selection with respect to formation. If you're drilling sand formation, what kind of lubricant do you use? If you're drilling shales, if you're drilling clay, what kind of lubricants do you use? If you're using OBM, it's advisable to use solid lubricant. You're drilling with WBM, it's advisable to use liquid lubricants. Lubricant conclusion, oil-based mud have lower friction coefficient than water-based mud. We all know that. Increasing the oil-water ratio leads to lower friction coefficients. Ester-based systems have lower friction coefficient. What we are saying here is the higher the oil in your mud, the lower your friction coefficient, the higher your lubricity. That's what we are saying in conclusion. Improving shale stability. The controllable parameters that influence the shale stability are drilling fluid, mud weight, well trajectory, drilling and tripping practices. For fractured shale stability, use effective sealing agents. Now, when we talk about shale stability, well stability, we have different things we use in WBM, OBM. What do we mean by well stability? We want to ensure that we are not having losses. We want to ensure that the well is even. We want to ensure that at this point, the overgauge is the same with the other one up. We don't want to have different overgauges. We don't want to have unnecessary washouts. What do we do to ensure that we have our well is stable? It is the responsibility of the mud engineer to do this because he has chemicals. Now, it says the influencing of shale stability are drilling fluid. Number one, drilling fluid, mud weight, well trajectory, and drilling and tripping practices. When we talk about the drilling fluid, what kind of fluid do you use for a particular formation? What is the well program? What is the well profile? What is the geology of the well? At so and so point, what fluid do you use? You don't go and use a WBM where you have shale. You don't go and use a WBM where you have gumbo shales. You want to use a WBM and you have gumbo shales. You want to use a WBM at a depth that is very deep and it is sand. The tendency of having instability will be there. Some places, the sand will be falling off. You have cavings in and out. You have fluffing of formations. You have fallouts like that. What do? First of all, you must use the right fluids. Your mud weight must be right. Your overbalance must not be much, such that it fractions the formation. That's why they do leak-off tests. They also do FITs, well integrity tests. FIT, formation integrity test, and they do leak-off test. What's the difference between formation integrity test and a leak-off test? From your seismic data, you know that this formation is at so and so. Let's use it in equivalent mud weight. This formation is at 16 ppg equivalent mud weight. That is the formation pressure. So you want to do FIT, formation integrity test, and you apply pressure before the drilling of that section. And you apply the pressure to 14 and see if it will hold. And you put it to 14, it holds. Okay, your FIT is 14 ppg equivalent mud weight. So you calculate, the drilling engineer will calculate the pump pressure, the flow, weight, viscosity, all those ones we add up. What will be the hydrostatic? What will be the ECD? So those ones are there, the mud weight. The well trajectory, if it is an high angle, a straight hole, deviated hole, how do you treat it? If it is during drilling and tripping practice, if they are drilling very fast, if they are drilling and then they are trying to achieve 60 degrees, at one point it is 65, at one point it is 60, it is 59, it is 62, like that. Before you know it, you have your stock pipe there. Before you know it, big cuttings will be coming out and you will think you're having cave-ins. It's a lie, it's not cave-ins. It's just like the angle is even, is not even. Some places it's 60, some places 62. As the pipe is not having contour the way they have drilled the well in so much contours. The pipe is straight. The BHA will be the drill collar and the rest. As the bit is cutting, they will be cutting off some other things by his side. And somebody would think that it is cave-ins. It's not cave-ins. It is drilling, bad drilling practice. Tripping, if they pull out very fast or running very fast, it will cause hole instability. Sweeps. I will just talk on sweeps since you already have your manuals. IV sweeps. You can pump an IVs, you can pump an high weight, like I said earlier, you can pump a low vis. IVs could be same mud weight, 10 ppg, the viscosity is 10 to 20 seconds higher or more. That's high vis. High weight, you're running a 10 ppg, you could go with a 12 ppg sweep. Remember, higher mud weight gives you more buoyancy. Low vis, you can pump a low vis, it will cause buoyancy, it will give the cutting some buoyancy, and you continue like that. You can decide to do it same volume. Sometimes you can go with a tandem peel, a low weight, high weight, low vis, same weight, low vis, same low vis, mud, running mud, low weight, high weight, low weight, running mud, depending on how you see the hole, depending on how you see the cuttings coming out. Slide 43 is it's a kind of a sweep formulation, and the all deviations. We have the ones for vertical holes, deviated holes. If you watch the sweep type, it's for vertical hole, it's better to use a high vis. For deviated hole, better to use a weighted. Also deviated holes, higher angles, you can use a tandem peel. As for horizontal wells, just go with tandem peel. High weight, sorry, low weight, high weight, low vis, high vis, things like that. And then we have operations, guidelines, hole cleaning while drilling. So I'd like to bring the class to a close here with cave-ins. Cave-ins are large particles that comes out. It is not caught by the drilling bits. It is not by the drilling BHA. It just comes from the well. It could be caused by so many things. It could be caused by mud weight. Some places you're drilling with it could be caused by imbalance or unsteady formation pressures. You're drilling at 2,000 feet. When by the time you go to 2,500 feet, the formation pressure has reduced. Definitely there will be cave-ins coming up from the top. If your mud weight is too low, cave-ins will be coming. If your flow is too low, cave-ins could be coming. So there are so many factors. If you're having unnecessary losses, cave-ins will come in. If you have fracture deformation, cave-ins will come in. How do you know cave-ins? They are different from the bead cuttings, and they are mainly larger. They are not well hydrated. They are not dry. They are just soft and wet. They will just be coming out bigger particles of different shapes and sizes. But definitely they are bigger than the drill cuttings. So I'd like to bring the class to a close at this point.
Hello, sir.
Any questions?
Yes, sir. Please, can we also classify technically a horizontal well as a deviated well? Can we also say it's a deviated well?
Come back.
Can we also say a horizontal well is also a deviated
Sorry,
well?
I mean, horizontal well.
Yeah, can we also say it's a deviated well?
No. Horizontal well is not a deviated well. It's purely horizontal. If you want to call it a deviated well, you know there's a classification of wells. We have the vertical wells, we have the deviated wells, and then we have the horizontal wells. Horizontal wells are purely 90 degrees. Now, you can call it a deviated well if you have a deviation before the 90 degree. You're drilling, you deviate, continue drilling, then you get to a point where you form the 90 degree. We don't want to call it a deviated horizontal well, but that is what it is. A deviated well stops when you deviate 70 degrees, 60 degrees, it goes down and stops there. But an horizontal well, when a deviated well continues and becomes horizontal, you are looking at the last part of the well. That is what you use in classifying that well. The last section, what is it there? Definitely before you do your deviation, it is vertical, but you will not call it a vertical well, right? You're drilling and your angle is 60 degrees. You're drilling, first of all, it will be vertical until you get to a point, you start kicking off. And as you start kicking off, you start forming angles until you finally get your 65 degrees or 70 degrees. You call it a deviated well. You will not call it a vertical well because the top is vertical. It's the point where the well ends is what you target.
Okay, sir. Please, please one more thing, sir. When we're having cave-ins, is there any other special thing that we can do to mitigate or to improve the mud or to improve the situation?
Now, when you're having cave-ins, first of all, make sure your mud weight is right. That is the first thing you need to do. Make sure your mud weight is right, because when you're having cave-ins, it means that your formation is coming up on you. Possibly your hydrostatic, your overbalance is not enough. Your overbalance may not be enough. That's why you're having cave-ins. Two, it could also be that the formation has been fractured as a result of when they were pulling out, tripping. And then three, inhibit your mud. Inhibit your mud very well. If you're doing a WBM, inhibit it. Your KCl polymer is there, and PHPA is there, glycol is there. If you're doing a OBM, your WPS is there. Ensure that you inhibit your mud. Your mud weight must be right, 1. 2, inhibit your mud. Then when you inhibit your mud, you have done all these things, you're still having cave-ins, it will now lie to the drilling department to see if the mud weight is right, if the overbalance is okay or not. Maybe they need to increase the overbalance by increasing the mud weight.
Okay, thank you, sir.
Any other question before I run? Any other question, guys, before I run off?
Excuse me, sir.
No questions from me, sir.
I thought slug is to be pumped before we pull out the hole.
All right, slug. Now, when I say I wait as a sweep. The phenomenon using I weight as a sweep is because increase in mud weight, the higher the weight, the more buoyancy effect it gives to cuttings. A bigger person exerts much more weight, more force than a slim person. Now,
but the slug
higher mud weight has more.
The weight of slug,
Come back.
The weight of slug, is it not too high for, I mean, to be
If the weight of slug is not too much for it,
yeah, to be introduced into the system.
For a sweep.
Yes.
Remember, it's in a dynamic situation. And then that slug too, the formation pressure will permit it. If the formation pressure does not permit it, it will be reduced. Remember, slug is 2 to 2.5 ppg higher than the normal mud weight.
Yes,
when they say high weight,
when it comes back into the system, it increases the mud weight. It will increase the mud weight if it goes back into the system.
Yeah, when they say high weight, yes, I'll come to that. When they say high weight, don't use the word slug. When they say high weight, don't use the word slug. High weight could be you're running a 10 ppg mud, it could be 10.5, it could be 11, it could be 11.5. Now, definitely it will increase the system. That's why you have your solids control equipment there. You have dilution, you have your centrifuge, all those ones are there. Some cases you can even catch it. You can even catch it. That's why you need to know the circulation time. You can catch it and divert it to your slug tank, plus a little volume. You pump 20 barrels. When it comes on surface, you just catch it. Bypass your sand trap, bypass every other pit, just push it into your slug tank. Take 30 barrels. You pump 20, take 30 barrels and continue. The effect will be very minimal. I tell people when your slug is coming up, don't wait until it gets to surface. As it is coming up, run your centrifuge. Start your centrifuge. 10 minutes before your slug comes, 20 minutes, 30 minutes before your slug comes, begin to run your centrifuge. If your centrifuge is not working very well, begin to bleed in base oil or premix. Or take some volume of your active away and bring a lighter fluid in. Take 20 barrels of what you pump out of your active and bring a lower fluid in. Bleed it in to regularize your mud weight. Don't wait for the slug to come up and cause problem for you. They'll feel that you don't know what you're doing. Any other, Baba? Okay, let's look at our faces again. I'll stop sharing my screen right now. Let me just look at our faces before we call it a day. You can put your video. That's Alex, keeping beds. All right, nice to see you. Nice to see you.
Thank you, sir. Thank you, sir.
Okay.
Please, I want to confirm from the class. What are we still on another lecture? I think this should be the end. Please, I want to confirm from the class.
Peter, is there any more lecture for them? For me, I don't have any lecture with you today.
For now, none yet. But I will communicate to them in the group.
Okay, like I said yesterday, my contacts are with Peter. You want to reach out to me anytime you are having issues or in other related topics. I'm just one call or one WhatsApp away. Like one Igbo man said, he told his instructor, if I have problem, you are one call away. I'll call you.
Thank you, sir.
Okay, guys, have a nice time. Have a nice day. Aji, I didn't hear your voice today. What's happening? Is he doing something else while he logged in?
Sir, I'm right here.
What's happening to your voice, Baba?
Sir? So,
Don't tell me he's stressed when you're on time off.
no, sir, you know, even the time off is never sufficient. It's just 2 weeks, and there's a lot of things to do in town before work resumes again. So,
Even if at all it's 1 month, it will
Guys,
not
I
even be sufficient.
need to go. I need to go.
Okay.
We'll talk later.
Okay, so thank you.